K8BYP with another poor quality but fantastic content video for your amazement and amusement. Another look at the reasons that antennas aren't resonant or shouldn't be if they are. I went over this in my antenna and transmission line series and maybe in the networks series, but I have seen absolute proof here with hundreds and thousands of contacts on the air to show the extreme difference in performance between a non-resonant antenna like mine, which are very wide in bandwidth, and the average ham antenna, which is very narrow, which are always described as resonant. My antenna is resonant. Well, if it is, A, it shouldn't be, and B, it's narrow-banded. There's a tuning fork. You might use that to tune a piano, but you can't tune a fish with it. Strike the end of the U-shaped fork on a hard object and hold the handle at the bottom, and it will vibrate at some specific frequency. We know that because we can hear it, we can feel it through the handle, maybe even see it if it's a very low frequency. An analogy to that is an RLC circuit in electricity. Question, are these resonant? What is resonance? According to the original paper by Julian Blanchard, we have the analysis mathematically of a series RLC circuit in this manner. Considering it's a series circuit and the current is the same through a series circuit, the current is the common, to misuse the term, common denominator. But on the left, the voltage across the resistor is characterized by R times I from Ohm's law, where big R tends to be a steady state or DC characteristic, and the small italicized tends to be an AC term. And notice R is big R. And this goes to show why R is not Z. There's no frequency component in there. The resistor acts the same regardless of the frequency. The center term L di dt from the differential equation V equals, and in the improper form C dV dt, because we're trying to work with current, that C dV dt has to be changed to be in terms of I. But that's not really important here. But what's described here is that R has no frequency component, but hiding behind these two differentials is the fact that these components are frequency sensitive. If we break that down to reactance, then we see the term omega, which contains the idea of frequency, because omega is 2 times pi times f in radial velocity. It's a rotating vector spinning at a faster rate, as we say, at higher frequency. And these components store energy, and when they are, as we say, resonant, they're swapping energy back and forth forever, except that the loss of the resistor consumes the energy and the system eventually dampens out. In that system, resonance occurs simply because of those components being there and those three terms in that big differential equation. The critical point with resonance is that resonance exists without doing anything. Energy is not a factor in resonance. That circuit would be resonant just because we can draw it on paper and solve for those three terms, which, by the way, that's an equation in Kirchhoff's voltage law, that there's an overall V equals, and of course Ri equals V, and V equals L di dt, and V is already in the C equation. But the key point here is that resonance doesn't do anything. It's like the English expression, a state of being. It doesn't do anything, it is something. It's a characteristic of those components in that combination without doing a thing. So therefore, it's immediately improper to say that something doing it, something active, is necessarily resonant, or that resonance is causing that action, because that's not quite true. Yes, it's involved with the action, but it is not the action itself. Now, when energy is applied to that system, it's applied in two different ways. In engineering analysis, there are a natural response and a forced response, perhaps a step input. Striking the tuning fork very sharply is just say a square function. It is sharply hit that bends one of the arms, and then the arm snaps back and forth and vibrates, and the whole thing vibrates. In the RLC circuit in classic electrical calculations, sometimes they apply a step function, a square impulse, which charges a network and thereafter something happens, or that network can be excited by its natural function, which is often taken to be sine. The components, the L and C, are not sine components, they're exponentials, but the exponential function is not continuous, except that it's continuous to infinity in one direction. So that's a better explanation yet of the difference between the exponential behavior of the components and the oscillatory or sine or cosine function of them working in the circuit. That's why that difference is there. But when these systems have energy added or are excited, they don't resonate, they oscillate. And that is the critical difference. The resistor is not the point. The L and C values are. And by virtue of those values having frequency response at one frequency, as Blanchard showed, there's a particular condition where that is the most efficient or effective. That's at resonance, that's at a single frequency in theory. And that's why resonant antennas are very bad, because they're only resonant at a single frequency. And these so-called resonant antennas might be 5, 10, or 30 kc wide, and hams are constantly complaining about them being out of tune. Well, that's because they're not made correctly, and maybe they are resonant, but they shouldn't be. And my antennas are not, and they're extremely broadbanded. And by virtue of that, they work far better. But oscillation is the swapping of energy back and forth between that inductor and that capacitor. That circuit can be forced through a forcing function to oscillate at almost any frequency. But there's only one frequency at which it is resonant, and that's the nature of filters and selective components like crystals. That's basically the schematic for a quartz crystal in a series mode. But how this applies to antennas, and I hadn't caught it before, is that, to back up a minute, that system can oscillate whether it's at resonance or not. But what's happening, and the difference between the circuit and the antenna, is that in the circuit, here and here, this oscillation is a result of an increasing magnetic field here and decreasing E field here, because energy is being transferred from the capacitor to the inductor. And at some point that process stops and reverses. The magnetic energy returns to a circuit current which charges a capacitor, and that back and forth is what the oscillation is. And it will go on forever, except it's bounded by the losses imposed by that resistor, and that's where we get the three cases of underdamped, critically damped, and overdamped. But we can't go into that here, don't have enough time. But again, that is not resonance, that is oscillation. The problem with antennas is they don't oscillate, because oscillation implies a conservative function, and with very low losses, this circuit is extremely conservative and will ring, so to speak, for a long time. Basically then bounded by the inductor spewing field off into space very slowly. The capacitor tends to conserve it entirely, except for a little fringing and some internal losses. But with no losses, this will oscillate forever. Antennas do just the opposite. They don't conserve diddly. It's either so-called radiated, or it's returned back down the feed line as what we call SWR. It doesn't oscillate. Well, how can we visualize that? Well, very simple. In an antenna arm with a traveling charge, that charge creates an E field if there's another charge out here for it to correspond with, for example, on the ground. Just the presence of a charge not moving makes an E field line. When the charge moves, conservation of energy says that the energy of the motion then becomes a magnetic field. But these two are not oscillating back and forth. They're the same animal. One's with the other in proportion to the voltage between that charge and there, and the magnitude of that charge's movement, making the magnetic curl. But this is not swapping energy back and forth from E to M fields, therefore there's no oscillation there. There might appear to be And there is somewhat of a periodic function if that's traveling out the end of a dipole arm and meets a reflection and comes back. But that isn't really oscillation and not really resonance. And certainly not in the case of the circuit, the series resonant circuit. Or if it is, it's my position, I keep hammering on this, it's best to not consider it that way, because that analysis gets messy. And this so-called transmission line model is a lot cleaner and easier to understand. And when I got huge gains in antennas is when I adopted this transmission line model and designed my dipoles with it, and the difference was absolutely jaw-dropping. Now, this idea that everything's resonant comes from the early days of radio, with radio operators adjusting plate and load on a transmitter, tube transmitter. And this saying is the plate is resonating. I showed in the network videos that looking from the load back, this network here, this mesh, is both series and parallel, but it is not resonant. Because if it's resonant, this point is an open circuit. It's close to resonant, maybe, in a parallel mode, but this is where the increase through the idea of conjugates. That's where the load resistance becomes stepped up through 2 steps to here, where that resistive value is the same as the source. And then this capacitor effectively cancels out in a series circuit the residual reactance at this node. That, strictly speaking, is series resonance, although the overall action in the circuit is not. And here's a challenge for you to see if you conceptually understand what's happening in the amplifier circuit. In practice, we adjust a plate control for minimum plate current. But in a series network, at resonance, the current is maximum. And I'll leave it as a puzzle to you to explain why this can represent a maximum current, but the correct adjustment of that to resonance results in a lower plate current. That's a very important step to master to understand amplifiers, because otherwise they'll be inefficient or damaged. So the key here is to understand that both this and the antenna arm are dealing with E and M fields, but these fields are essentially contained within the component and they are separate. These are not. These are a very different configuration, and there is no oscillation back and forth between that and that. And here's where the definition of an antenna comes in. This, as a result of the feed point being excited by a voltage, represents E and M fields, what we call near fields of the antenna. And then later, when this energy is spewed off into space, then it's represented as a field, a set of fields oscillating back and forth between E and M. But that's not what's happening here, or not fundamentally. And what happens in between those modes, if you will, is what the real antenna function is. So there's quite a mouthful. I hope it was tasty. KBYP did it.